Okay, so this video is going to cover some of the really important theory that's going to help you do the experimental design experiments, to help you design a workup procedure that allows you to separate and purify these three compounds using a liquid-liquid extraction. Okay, so there's a bit of background theory that you need to know, because what you're doing is you're applying this theory to design your purification. Okay, and it's teaching you the skills to be able to do this. Some of the principles around solubility, like knowing which things are going to dissolve in the organic and the aqueous layer, that was covered in the iron experiment video. So you want to re-watch that if you're unfamiliar with any of the theory, solubility and recrystallization from there. And in terms of explaining how a liquid-liquid extraction works, you should watch the esterification theory video, which explains those things. This video is going to focus on the additional theory that will help you design your purification, okay, which is going to cover acid-base theory. So it's about knowing if you're using a certain acidic or basic solution, is it actually going to deprotonate or protonate your molecules to change whether or not they go in the organic or the aqueous layer. Okay, so what you're doing in this liquid-liquid extraction with this purification is you're going to have to manipulate how an organic compound dissolves in the organic or the aqueous layer. And the way you're going to be able to do that is with certain functional groups, because with certain functional groups you can either deprotonate them, like carboxylic acids and phenols, into their salts, or you can protonate them, like amines, into their salts. And if you've got the salt form, you can get these molecules to dissolve into the aqueous layer. And if you have these molecules in the neutral form, you can get them to dissolve in the organic layer. They're organic soluble. Okay, so you need to work out which aqueous layer you're using at a particular stage of your purification to decide and manipulate if your organic molecules want to be in the organic or the aqueous layer. And the way to do that is to think about the pKa values of your functional groups in your molecules, and also the pKa values of the aqueous solutions that you're using. So first, what I'm going to do is sort of introduce the main concepts about what pKa actually is. So with every molecule that's an acidic or basic functional group, we have an equilibrium between the form of the molecule where you've got the protonated, the acidic form, where you've got the proton. So here it's with a carboxylic acid, it's where it's a protonated carboxylic acid, and where that proton can be deprotonated and it can dissociate into H+, leaving you with the rest of the molecule as its anion. And the other form, the carboxylate form here that we have, is what we call the conjugate base form of this molecule. Okay. Now, depending on the functional group that you have, certain anions are going to be more stable than others. So, for example, in this carboxylic acid, it can sort of delocalize its electrons around the two oxygens, and that makes that anion relatively stable because it can spread that negative charge. And so what pKa can do is it gives you an idea of how acidic a molecule or basic a functional group or a molecule is, and therefore how easily can you form a molecule in its sort of conjugate base form, where you've deprotonated it and it's in its anion form, or how much of it exists in its protonated form. What you do with pKa is you get a number, a numerical value of the strength of the acidity or the basicity of the functional group. So with this carboxylic acid, for example, what happens is in this equilibrium process, where you're dissociated between the acid and the conjugate base form, okay, at pH 5, we can get an equal mixture of the acid form and the conjugate base form. And at this particular pH then, this leads to the pKa values. So the pKa values come from the particular pH you have of a molecule when it's dissociated into its acidic and conjugate base form in equal amounts. So for this functional group, carboxylic acids, it's around about pH 5 that you get an equal mixture of the acid and the base form. And so we say that carboxylic acids have a pKa value of 5. So this is slightly lower than neutral pH, pH 7, which means that carboxylic acids are weakly acidic functional groups. It means that it quite easily sort of readily deprotonates into its conjugate base form, and if you want to get more of the acid form, you need a more acidic solution, something that's lower than pH 5 to get it to exist in its acid form. If we do amines as well, what we can see is when we think about an amine or a basic functional group, we think about the protonated form being the acidic form because it's the one that contains the proton, and when it's dissociated and gone back to its neutral form and dissociated to leave H+, then we think of the amine, neutral amine, being the conjugate base form. And so the pKa of an amine, when it sort of dissociates in equal amounts, like so, into the acidic and the base form, is around about pH 10. So we say that amines have a pKa value of about 10. And this means that amines are weakly basic molecules because pK of 10 is higher than pH 7 neutral PN. It's more basic than pH 7. So what this means is that if we want to protonate our amine, okay, then what we need is to use something. We need it to have a pH lower than 10. But if we want to neutralize our amine, we need to give it a pH, make our aqueous layer have a pH that's higher than 10. Okay, so that's the general principle kind of summarized in this slide. If we take the pKa values, we know what they are for a particular functional group. If we want the acidic form, okay, we want the lower pH than the pKa value. If we want the conjugate base form, we want a higher pH than the pKa value. Okay, and so what we can do is we can think about the pK values of the solutions that we are using in the aqueous solutions that we're using in the lab. It's going to be our aqueous layer, and we can think about how that's going to manipulate the pKa values of the functional groups that are going to be present in the molecules that you're trying to purify. So, for example, if we're using 2 molar hydrochloric acid, okay, it's going to have all these molecules, all these functional groups in the protonated, the acidic form. So for the phenol and the carboxylic acid, that will be the neutral form, but for the amine, it's going to be the acid, the protonated salt form. Okay, if we want to, if we use something like saturated sodium bicarbonate, for example, well, what that's going to do is it's going to deprotonate functional groups and have them in their conjugate base form. So the carboxylic acid would be deprotonated, the phenol would be deprotonated, the amine would be in its neutral form as well. Okay, so think about this, think about pKa and therefore how it's going to manipulate the solubility of these compounds in the solution, in the solutions in your purification. Okay, so as kind of shown here, okay, what we're trying to do is separate this amine and this amide. Okay, the amine has a functional group that can be protonated. It's got a pKa of 10. Okay, so we wash with 2 molar HCl. It's got a pKa of -7. Well, that's going to protonate all of the amine into its salt form, so it can go into the aqueous layer. That leaves the amide into the organic layer, and then we can wash, separate that organic layer, just dry the layer and remove the solvent to give you that pure amine. Okay, so it's using those principles of pKa. We can sort of work out and think about how much our compounds are going to be protonated and deprotonated, and therefore how it's going to be manipulated into the organic and aqueous layer. And that's what you need to do now with regards to designing your purification for your 3 molecules. Think about the pKa's of the key functional groups you can see here, which can be protonated and deprotonated, and design a flowchart to demonstrate your purification and how things will be separated and changed in each layer.